Anthropic released Sonnet 5 yesterday and Fable week before. Every week, new frontier models are coming out. Winners in this AI race are not the ones using best models, but those who have the best harness and systems around them. Today, we will be covering one of those systems, an SDK and MCP released by FlutterFlow. I promise you, if you stick by this video, you will understand how system design of these production grade agentic systems work and how you can implement them for your own system. So let's get into it. So most of these agentic systems, and this is not limited to just FlutterFlow or any, most of these agentic systems, especially if they are right systems, have this flow. Simply you deploy an agent takes up the task which it is given to, it calls the harness, it calls the tools, it gathers context, explores, and then it writes, and then the run engine works, it validates, it pushes, and now it's live. So let's now go by module on how this specific engine has been built. So let's start with the module 0, which is the genesis. So what usually happens is that whenever you go into a repo or you start developing, the first thing you do is that you initialize and start and basically pull in the boilerplate released by the framework. So in Node you do npm init. Well, in Flutterflow case, to initialize the to basically pull this AI server, what you do is that you run this command. And what basically this does is that it is further divided into three phases. So the phase one is basically in which init underscore visit.dart is involved. Now what is this? Now this is basically you can think of as a Dart a Dart code which basically interacts with the CLI, and it basically captures the flags and inputs of the user. So this usually are your app name, your project ID, your API keys, stuff like that. The next phase is basically one of the most essential ones, and that is to basically pull in the boilerplate slash scaffold. So first of all is the make workspace, in which we basically scaffold or pull the boilerplate via SDK, which is obviously first, and then we have installations. So first is the vendor engine, which is basically installing the SDK AI SDK itself, and then it is basically the workspace, which is a verification step in which we reinstall it on the root, because this is not this vendor workspace run is not downloading internal dependencies like HTTPS or crypto. It is basically re-downloading or downloading the SDK itself, and then we write envs, project IDs, API paths, and then the phase 3 is basically in which we do two things. First is we check if the project ID has been passed. If that flag has been passed, we basically pull in the backend, and if not, we just use the boilerplate. And then the first agentic step, which is to basically initialize the config files, which in case of Cloud Code we have .mcp.json. In Codex we have the config file, and in Gemini we also have its own configuration file. So it writes that. So the next module basically covers the orchestrator, and over here we basically this part is basically when you start an agent. So when you start Cloud Code in this case, or when you start Codex, what exactly happens? So what exactly happens is that inside those config files we have this this command which the agent always runs. So before we get into this, let me just go through some of like really um, like a very important process and very important terminologies and flow before we get into the depth, and that is how these processes work. So basically, Cloud Code Session, FlutterFlow Server, MCP, CLI, all of these are processes, and processes have three channels. One is the std in, std out, std error. So how these engines work, how the MCP works is usually people think that MCP itself is the engine. MCP is just an orchestrator. So the agent, which is the brain, it decides, okay, I need to call MCP for this. It spawns a process, MCP server, and that MCP server basically interacts with the harness, which is an SDK, which in this case is an SDK which we're working with. So the input of the agent is given as sorry, the output of the agent is given as input to the MCP server and the engine. The engine then basically runs the entire process, and it basically computes, and it basically the output of the engine as well as MCP server then is shifted back to the agent, and this is how this orchestration works. It's completely similar in this. We have a server Dart which basically runs this orchestration, and first obviously it checks for the flags which have been passed via config, maybe such stuff like read only, so there is no write access there is, we block the agent to write anything. It loads the credentials which is used to push back code. It cds into the directory, so it's in the right direct, so it has access to everything, and it opens a pipe which is basically you can think of agent and a sub process which the agent controls, not the user, which in this case is our server file. So the step two is the after post pipe connection, we have the basically the agent and the server, they communicate via a protocol known as JSON RPC, which basically you can think of it as Claude uh, communicates to server, it initializes, the server then communicates back to Claude, it tells it its capabilities. Uh, the Claude then asks for a list of tools, and the server basically retrieves them and sends them to the agent, which gets context. And when actual calls do happen from the agent to the server does that and gives the output from the engine. Then we have the step 3 in which after the post handshake, everything has been connected, the tools have been enabled for the agent to use. We have 4 sets over here. So we have a read set, read inspect set, in which we have tools like status, search, inspect, resources. We have knowledge slash setup module, in which we have tools like docs, history in it. We have we have a write module in which we have two. These are very important ones. We have the run and the patch. These are basically the engines which I was talking about, and we will get into these. We have a check, which basically validates, and dry runs DSL. So let's go into the next module, which is the mirror, and here we are interacting with with basically you could say uh, it's basically, you can think of it as pulling the project and mapping it so the agent can interact with it and read from it, and basically acts as its contextual memory. So basically you can think of the way how they have made this is, you can think of it as a classic ETL. Now, what is an ETL? It's really important we learn this. So ETL is basically a data engineering process of extracting raw data and making it uh, according to your system. It is used by uh, it is used to handle extreme amount of data in a very linear process. So it has basically 3 processes, which is extract, transform, and load. Or extract is the bronze layer, transform is the silver layer, load is the gold layer. So basically on extract we get the project. In the transform layer we basically map that project out, and in the gold layer we basically um, incrementally we use an incremental process to make sure that we are not, we are not pushing or uh, making a snapshot of stale data. So everything's fully up to date for the agent to use. So we basically get the project by doing by in which the server basically runs a post request to the FlutterFlow's server to get the project, passes the project ID. Now the response we get is something very interesting. We basically get a proto buff, which will be encode it uh, into gzip plus base64 encoding, and obviously the timestamp of its updation. And now, what is this FlutterFlow project proto? This is basically an entire app as one structured binary object, a blob. It has pages, components, widgets, actions, themes, everything in it. And why not use JSON and all of that for it? Because Protobuf is basically made by Google. It is a compact, strongly typed binary data format. And basically, the overall flow here is that we pull the FlutterFlow project. It is encoded into an object. The compressed blob is sent. It is decoded. It is stored in memory locally, and we generate many small files from it. So step two is exactly that, in which basically we have this specific function which is build type project SDK sources. It takes in proto, it walks it one by one, and it emits different files, which it emits projects.dart, schemas.dart, apis.dart, pages.dart. Uh, so in the next step, which is process of writing entities. So here things get interesting, and here is a very nice system design, which is basically making sure that we are not working with the stale data. And here we use an incremental approach for this. So for each file there is a SHA, which is you can think of as a very long hash. In encryption, it's an encryption algorithm, and a timestamp. So SHA is compared. How it is compared, we have a project underscore SDK underscore meta.json. It's a very massive file, and it basically has everything in it. It has the SHA of each file, the path of each file, and basically this is compared. And if it is unchanged, we just skip it. If it is changed, we basically write the file, and we basically write the entity. And if the path has changed, we delete the old and write the new entity with the correct path. And if it existed before, now gone, we just delete it. Another important thing to know is that agent doesn't call MCP tools to get Dart files. It's always present on disk, so it just gets it by just using its turns or by grepping. Now let's move to the module 3, which is the blueprint. So here we are working with DSL engine, and we have two files, which is the DSL slash create.dart and DSL slash edit.dart. This is one of the most important modules of this entire system. So what is a DSL before we get into it? You can think of DSL as a domain specific language. We use it everywhere. You can think of it as a very specific tailored language for a specific job. For example, SQL, it's used for querying database, Terraform, describing cloud infra, HTML, CSS, describing web pages. There are two types of DSLs, which is an external DSL and it is an internal embedded DSL. In external DSL, we invent a completely brand new language and its parser like SQL, where we have internal embedded DSLs in which we basically use, like, for example, Dart, but have our own specific classes and functions, just like how FlutterFlow AI SDK is using. Why it is used? So it gives us type safety. LLMs are usually pre-trained on these languages, as well as devs ease and familiarity. So I will go through the edit process because both of these processes are very similar. They just have a different purpose. So for example, if you want to add or edit a dashboard page to an existing app, they both use the edit flow. They do not use the create flow. This is a little bit of confusing part. So what it happens is that first LLM has to build context. It basically runs through the generated code, or it basically checks the library which generated code. You can think of it, it's a complete runnable code. We will cover this too. And the library lib slash flutterflow we just covered. And then basically it reads and quick trains itself via learning. So we have patterns and references. These are pre-made folders full of boilerplate code from FlutterFlow, which the model can use to understand how to work with DSL and what to do and what not to do. Patterns, you can think of it as ready-made complete features like auth flow. References are tiny operations or tweaks like buttons. So the LLM edits. So basically, when we go into the DSL edits or start, it's a huge, it's a file, and most of it is functions which run on complete with execution. But the only thing which LLM interacts is specifically with this function. Here it edits and writes the thing which we need to writes the feature, and then LLM calls the run MCP tool, which basically passes in the file as well as project ID as well as commit message. And then obviously the server handles this. The server, as you know, the MCP tool is just the orchestrator. The server checks for the API key. This handler checks for the API key, translates the flag pass, and run this FlutterFlow CLI tool. Now over here, basically you can think of it as we run this entire file, and when we run this file, we basically first the DSL added dart. It first checks, runs this function which checks for the flags and validates them, and then the FlutterFlow's internal engine works, which we'll get into, in which it builds, compiles, validates, and if validation success, it pushes back. The create process is very same. It's just that it basically runs when we are making a new project, and and the function is, the function's name is just different. It's build starter create flow. But yeah, so we have two cases here. If it's a very structural change, this entire engine runs. If it's a very minute change, we use another tool by the name of patch, which we covered, in which DSL is not even involved. It's a very quick change, and it's pushed directly. Okay, so now we get into the very important part, and which is the internal engine and how this entire push flow works, and how agentic systems basically make sure how these MCP systems are made very low level. So as we mentioned that we had these functions in in basically the server side, which is FlutterFlow AI build starter edit flow or build starter create flow, which is basically the files inside, these are these files inside the edit and create dart or FlutterFlow AI run. So basically how this entire process run on this tool call is, it's a 9-phase transactional pipeline for system run. First of all, we resolve the target. We um, find what the project is, what if it's a new project, if it exists. Then we do the pull, and in which we basically do is that again we use the SDK to get the project, we get the prototype and timestamp which we covered. We snapshot this current system and save this prototype protobuf before tasks. Now apply tasks. So now whatever we have changed, what happens is that we start mutating the pulled protobuf which we recently pulled and saved, and we apply the DSL changes to it, and it is compiled. Now validate tasks. What happens here is that SDK runs a validation check. If there are errors, we list the failed tasks and the push is blocked. And it again can be run locally via dry run, depends upon the flags which are passed after validation. Then we have a gate. Now what gate is basically a check between the push and validate phase. It only runs if only runs on two things. One is that if the validation is successful and the dry run flag was false, the intention is to push. Now this is an interesting part in which we check for conflicts as well as rebase. So what happens is that we grab the baseline updated at MS timestamp of project change. We get it via metadata which we pulled via from the protobuf. If it's the same, then it means that there is it's safe to change, safe to push. There has nothing been changed. If it is different, that means someone made push change something. So what we do is that we check for the diff, and if the diff is different, then it is safe to push. We rebase on top of the changes and push. If it is same, then we have conflicts and we just stop. And then we have the push. So in case of push, we first basically here is finally that the validated mutated proto is pushed to the server via SDK push project, and we basically get a commit ID from the FlutterFlow server as well as expected updated. Now what this is basically a server guard to make sure that make sure the local and the remote are synced, and then we upload happens here is that or DSL, um, we have archive. So basically, what happens here is that the DSL is pushed to server as well as archived locally, and we have refresh records in which we again at the end of this we record this entire thing, and obviously we refresh context because now the project has been stale locally. Some important things to discuss is that in AI SDK FlutterFlow harness there is no rollback like Git. The only two options you have is to do a forward fix, which you fix the error or the bug, or use version history via FlutterFlow platform to revert it. So every run records a run ID. Either the engine trigger is either the engine runs or fails. If the run is pushed, then the run ID is the commit ID by server, else it's just a timestamp. And every successful run basically archives the DSL which we covered and commits, and it basically records. So we have three in which we basically in this type of folder we cover the full transcript of the run. This is the one in which the precise DSL which has been run, and this is a massive JSON L file in which is used by LLM to basically get it's a one line JSON summary of what has been what's the timestamp has been, run ID, and all of that stuff. So FlutterFlow AI support replay basically rebuilds the fresh workspace to reproduce this run to debug. We have so also the pulls do not touch or update logs. We have AI history with run ID. It lists run recent runs. Without it, just prints source from history. Okay, I'm sorry about this. Actually, without it basically lists runs, and with run ID, it prints source from history. So this is a little bit, you can think of it, this is alternative. And then we have covered the major parts of it, and now we only have is the ground truth, which is again the generated code. This is a full runnable Flutter app. Uh, Basically, how it is produced is during each pipeline run and phases we produce it, or you can do it on demand using refresh context or codes and fresh tool calls. Then we have a module of dry running, which is the testing, in which we have this specific file, which basically what you can do is to just dry run and compile that if it runs locally and test before you push. So what agent does is that agent edits the DSL and compiles the proto locally, and you can use it via CLI command, not the tool call. So this is basically the whole system design of FlutterFlow's AI harness and MCP and how usually the agentic systems are made. Do feel free to let me know if there's any other system you would like me to cover, and if you need help in implementing these systems or a custom solution, please feel free to communicate to me. I'll be more than happy to help you. I'll be more than happy to help you. And thank you and have a nice day.